let's say college-aged male. That'd be a good example. Let's say if your lactate threshold pace was 6 minutes a mile. Okay? If you're running at 6:30 pace, okay, your lactate threshold is 6 minutes a mile. If you're running at 6:30 pace, are your leg muscles producing lactic acid? Yes. What if I said you are lying down taking a nap? Are your legs producing lactic acid? Technically, yes, not a lot, but lactate is being produced all the time. Glycolytic metabolism is always on. Okay, at 6:30 a mile, if your lactate threshold is 6 minutes a mile, running-wise, would you be accumulating lactic acid at that pace if you're running 6:30 a mile? You got to think about it. Is 6:30 faster or slower than 6 minute pace?
Slower.
It's slower. Okay, so would you be accumulating lactic acid at 6:30 a mile? No. Okay, because you'll be able to remove it faster than you're producing it. How can you remove, how does lactate get out of a muscle? Okay, lactate's produced in muscle. How does it get out of the muscle into the blood? Do you remember? Well, that's how you can remove it from the blood. Non-exercising skeletal muscle can remove it from the blood. The liver can remove it from the blood. But how does it actually get out of the muscle? This is the thing we talked about in our last class. Now, there's proteins in your muscle called MCTs. Remember MCT proteins? Those increase with training. Those help you remove lactate from the muscle. When you remove lactate from the blood, generally there are two primary ways it's removed from the blood. Two primary fates. Okay, one we said was non-exercising skeletal muscle can convert back into pyruvate, be metabolized by the Krebs cycle. What's the other way that you can remove lactate from the blood? What happens in the liver? Yeah, gluconeogenesis. You take two lactates, sandwiches them together, makes a 6-carbon glucose. You make glucose from lactate. Remember that? Okay. Let's see. Measuring energy expenditure with indirect calorimetry. Let's say I wanted to know how many calories you burn at rest. How could I actually, what would I have to physically measure? I could put you in a chamber and measure your heat production, but that's not really practical. If we did indirect calorimetry, how could I measure how many calories you burned at rest? What would I have to actually measure from you? Okay, what if I measured your VO2? Would that be helpful? How much oxygen you consumed? Yeah, I'd have to know that for indirect calorimetry, but I'd have to know something else as well. RER, and what's RER defined as?
Respiratory exchange.
Yeah, that's what it stands for, respiratory exchange ratio. And what's the definition of RER? It's equal to, mathematically speaking, VCO2 divided by VO2. VCO2 stands for the volume of carbon dioxide produced. Okay, so I'd have to actually measure, besides VO2, I'd have to measure VCO2. And once I know those, I know your RER. And why do I have to know RER to determine energy expenditure? Why is RER important? It tells me what? That's correct. It tells me what substrate I'm metabolizing, how much carbohydrate and how much fat is being metabolized to produce ATP. If RER is closer to 1, it means I'm metabolizing mostly what? Or primarily carbohydrates. If it's closer to 0.7, I'm metabolizing mostly fat. Okay, so once I know RER, I can then determine which substrate I'm metabolizing. And remember that chart? That chart tells us how much oxygen, how many kcals are produced per liter of oxygen consumed. I multiply that by VO2, and then I get kcals that I would produce per minute. And if I want to know resting, I can multiply it by whatever time value to get an hour or 24 hours, so on and so forth. Okay, when we do that, we're measuring energy expenditure. We do indirect calorimetry. I'm measuring calories produced through oxidative metabolism or glycolytic metabolism. When I'm measuring oxygen consumption and CO2 production, we're talking about oxidative metabolism. So we're talking about aerobic sources. Okay, aerobic energy expenditure. If I want to measure anaerobic energy expenditure, is there a completely accurate way to do it? Technically, not exactly. There's not a completely accurate way to do it. Early researchers thought oxygen debt might be a measure of it. Okay, and remember, after exercise, there's this extra oxygen you'll consume above resting levels. That was called HPER, which stands for excess post-exercise oxygen consumption. Remember that? Okay, what are some reasons why after an exercise bout your metabolic rate, your oxygen consumption is elevated over resting levels for a period of time afterwards? Do you remember that? We did this like 2 days ago, I think, or 2 classes ago. You had this extra oxygen you consume. What are some causes of why your metabolic rate, your oxygen consumption is elevated once you stop an exercise bout for a period of time?
Your temperature's still elevated?
Yeah, your temperature is elevated, and that causes several enzymes and metabolic processes to run faster at a higher rate. Okay, what about heart rate? What about heart muscle, heart rate, and breathing muscles? Are they going to be elevated slightly for a period of time once the exercise stops? Yes, and they'll consume ATP, requires oxygen consumption to do that. What about metabolizing lactate, or the process of gluconeogenesis? Okay, those things, yes, will involve ATP. There's also reloading phosphocreatine. In the first 10 seconds or so of your exercise, your phosphocreatine is going to be depleted. We have to reload that. That's part of it. You also are running sodium-potassium pumps. There are all sorts of good things in there that we talked about that happen. What are some things that cause EPOC to be higher after an exercise bout than another exercise bout? Let's say if your goal was to, after the exercise bout, you wanted that EPOC, which I've talked about as being free calories somewhat. If you wanted that to be higher, what could you do to the exercise bout to make it higher? You could increase intensity, and you can also increase duration. Both of those things cause that EPOC, extra oxygen consumption, to be higher after